Welcome to APCV 320, Computational Thinking and Doing. In this module, we will discuss programming languages. Lecture slides were adapted from Professor Henry Wershon, Applied Computing and Computer Science Program Director, who taught this class during the fall semester of 2020. We will be covering Chapter 6 from Brookshire book, Computer Science and Overview. From Chapter 6, we will be covering just the first 5 sections. We are not going to cover the latter two, 6.6 and 6.7. They are mentioned in light gray color here, although I do encourage you to read through those sections to have a better understanding. Programs for modern computers consist of sequences of instructions that are encoded as numeric digits and ultimately binary bits. Such as encoding system is known as a machine language, the first generation language. Writing programs in a machine language is a tedious and error-prone task. In the 1940s, the programming process was simplified by developing mnemonic-based notational systems. These mnemonic systems are collectively referred to as assembly languages. Assembly languages were so innovative that they became known as second-generation languages. The primitives used in an assembly language are essentially the same as those found in the underlying machine language, the difference being the syntax used to represent these instructions. Thus, a program written in an assembly language is inherently machine-dependent on the underlying hardware and its specific capabilities. This hardware dependence was not conducive to software development. So this led to the development of a third generation of programming languages that differed from previous generations in that their primitives were both higher level instructions expressed as collections of underlying machine instructions and machine independent. As for the machine independence, reality has not proven to be this simple. When a compiler is designed, specific characteristics of the underlying hardware are sometimes exploited by the language being translated. For example, the different ways in which machines handle I/O operations have historically caused the same language to have different characteristics or dialects on different machines. It's often necessary to make some minor modifications to a program to move it from one machine to another. Consequently, computer scientists strove for more powerful abstractions that would allow humans to program without concern of underlying hardware differences. As an example of an instructions that can be represented in mnemonic rather than in numeric form, consider a typical opcode such as move R5, R6, MOV R5, R6, which means move from register 5 to register 6, which would represent the machine language instruction 4056. Although this machine language instruction may be confused, as the mnemonic opcode might suggest, it moves the contents of register 5 to register 6. More useful descriptive names are used to refer to the registers or memory cells. Such descriptive names are often called program variables or identifiers, as we will see in a couple of slides with an example. The primitives used in an assembly language are essentially the same as those found in the corresponding machine language. The difference is simply in the syntax used to represent them. Thus, a program written in an assembly language is inherently machine-dependent. That is, the instructions within the program are expressed in terms of a particular machine's attributes. Consequently, a program written in an assembly language cannot be easily transported to another computer design because it must be rewritten to conform to the new computer's register, configuration, and instruction set. Once mnemonic systems were established, programs called assemblers were developed to convert mnemonic expressions into machine language instructions. Thus, rather than being forced to develop a program directly in non-portable machine language, a human could develop a program in mnemonic form and then have it converted into a machine language by means of an assembler. As a more extensive example, the machine language routine, consider the machine language sequence of instructions on the left. 156C, 166D, all the way down to C000, which adds the contents of memory cells 6C and 6D, stores the results at location 6E, and then halts. It might be expressed in assembly language as shown on the right. LD R5 price, LD R6 shipping charge, ADDI R0, R5, R6, ST R0 total cost, then HLT. Note that LD, ADDI, ST, and HLT are used to represent load, add, store, and halt. Moreover, we have used the descriptive names of price, shipping charge, and total cost to refer to the memory cells at locations 6C, 6D, and 6E, respectively. Such descriptive names are often called the program variables or identifiers. Note that the mnemonic form, although still a bit confusing, does a better job of representing the meaning of the routine than does the numeric in the machine language form. Given the limitations of assembly languages, computer scientists began developing programming languages that were more conducive to software development than were the low-level assembly languages. The result was the emergence of a third generation of programming languages that differed from previous generations in that their primitives were both higher level, in that they expressed instructions in larger increments, and machine independent, in that they did not rely on the characteristics of a particular machine. Fortran and COBOL are two well-known examples of third-generation languages. Fortran, which stands for Formula Translator, developed for scientific and engineering applications. COBOL, which stands for Common Business-Oriented Language, developed for business applications. The approach to third-generation programming languages were to identify a collection of high-level primitives in which software could be developed. Each of these primitives was designed so that it could be implemented as a sequence of the low-level primitives available in the machine languages. Once this collection of high-level primitives had been identified, a program called a translator was written that translated the programs expressed in these high-level primitives into machine language programs. Such a translator was similar to the second-generation assemblers, except that it had to compile several machine instructions into short sequences to represent the activity of a single high-level primitive. Thus, these translation programs were often called compilers. An alternative to translators, called interpreters, emerged as another means of implementing third-generation languages. Interpreters were similar to translators except that they executed the instructions as they were translated instead of recording the entire translated version for later execution. That is, rather than producing a machine language copy of a program that would be executed later, an interpreter actually executed a program from its high-level form. The approach to classifying programming languages is based on a linear scale, figure 6.1, on which a language's position is determined by the degree to which the user of the language is freed from the world of machine-specific instructions and allowed to think in terms of the problem being solved. In reality, the development of programming languages has not progressed entirely in this manner, but has developed along different paths as alternative approaches to the programming process called the programming paradigms have surfaced and been pursued. Consequently, the historical development of programming languages is better represented by multiple tracks as shown in this figure, in which different paths result from different paradigms emerging and progressing independently. In particular, the figure presents 4 paths representing the functional, object-oriented, imperative, and declarative paradigms, with various languages associated with each paradigm. Although we refer to these as programming paradigms, these alternatives have ramifications beyond the programming process. They present fundamentally different approaches to building solutions to problems and therefore affect the entire software development process. In this sense, the term programming paradigm is a misnomer. A more realistic term would be software development paradigm. In the remainder of this lecture, we will be covering in detail each of the four listed software development paradigms. And here they are. The imperative paradigm, also known as the procedural paradigm, one defines the programming process as development of a sequence of commands that, when followed, manipulated data to produce the desired results. In a functional paradigm, a program is viewed as an entity that accepts inputs and produces outputs. In a declarative paradigm, one describes the problem to be solved rather than an algorithm to be followed. More precisely, a declarative programming system applies a pre-established general-purpose problem-solving algorithm to solve problems presented to it. In an object-oriented programming (OOP) paradigm, a software system is viewed as a collection of units called objects, each of which is capable of performing the actions that are immediately related to itself, as well as requesting actions of other objects. Together, these objects interact to solve the problem at hand. Functional programming versus imperative programming. As an example, this figure shows how a function for balancing your checkbook can be constructed from two simpler functions. One of these called findSum, which accepts values as its input and produces the sum of those values as its output. And then the other called findDef accepts two input values and computes their difference. The structure displayed in figure 6.3 can be represented in the Lisp programming language, which is a prominent functional programming language, by the expression. You have a parenthesis here, and then you have findDef, another parenthesis, findSum, all balance credits, close parenthesis, another parenthesis, findSum debits, close parenthesis, close parenthesis. The nested structure of this expression, as indicated by the parenthesis, reflects the fact that the inputs to the function findDef are produced by two applications of the findSum. The first application of findSum produces the results of adding all the credits to the old balance. The second application of findSum computes the total of all debits. Then the function findDef uses these results to obtain the new checkbook balance. For the same problem of balancing a checkbook, we can write the following pseudocode program by following the imperative paradigm shown on the left. Generally, a program consists of a collection of statements that tend to fall into three categories: declarative statements, imperative statements, and comments. Declarative statements define customized terminology that is used later in the program, such as names used to reference data items, which could be constants, literals, and variables. Imperative statements describe steps in the underlying algorithms, including expressions and control mechanism, or more abstract and reusable concepts such as procedures, modules, and libraries. Comments are somewhat self-explanatory, although we will discuss in a bit more detail. Normally, an imperative program or an imperative program unit within an object-oriented program can be thought of as having the structure depicted in this figure. It begins with a collection of declarative statements describing the data to be manipulated by the program. These declarative statements are then followed by imperative statements that describe the algorithm to be executed. High-level programming languages allow locations in main memory to be referenced by the descriptive names rather than by numeric addresses. Such a name is known as a variable, since when changing the value stored at the location, the value associated with the name changes as the program executes. Unlike Python, the example languages we will next review require that variables be identified via a declarative statement prior to being used elsewhere in the program. These declarative statements also require that the programmer describe the type of data that will be stored at the memory location associated with the variable, i.e., a data type. A data type encompasses both the manner in which the data item is encoded and the operations that can be performed on that data. For example, the type integer refers to a numeric data consisting of whole numbers. Operations that can be performed on integer data include the traditional arithmetic operations and comparisons of relative sizes, such as determining whether one value is greater than the other. The type float, sometimes called real, refers to numeric data that might contain values other than whole numbers. Operations performed on data type of float are similar to those performed on data of type integer. The activity associated with adding two items of type float differs from that for adding two items of type integer. Other common data types include character and Boolean. The type character refers to data consisting of symbols such as ASCII or Unicode. Operations performed on such data include comparisons such as determining whether one symbol occurs before another in alphabetical order, testing to see whether one string of symbols appears inside another, and concatenating one string of symbols at the end of another to form one long string. The type Boolean refers to data items that can take on only the values true or false. Operations on data of type Boolean include inquiries as to whether the current value is true or false. Again, as a reminder, being object-oriented Python does not require that variables be declared or typed. Every variable in Python is an object, which we will cover later in this course. And here are some examples of each of the previously described data types. The first three examples are type definitions, whereas the final example also assigns an initial value as part of the type definition. Dynamically typed languages like Python allow variables to be assigned without first declaring their type. Such variables are checked for correct type later when operations are performed upon them. In addition to data type, variables in a program are often associated with a data structure, which is the conceptual shape or arrangement of data. For example, text is normally viewed as a long string of characters, whereas sales records might be envisioned as a rectangular table of numeric values, where each row represents the sales made by a particular employee and each column represents the sales made on a particular day. One common data structure is the array, which is a block of elements of the same type, such as a one-dimensional list, a two-dimensional table with rows and columns, or even tables with 3 or higher dimensions. For example, this figure displays the conceptual structure of two-dimensional arrays of integers having 2 rows and 9 columns. Once an array has been declared, it can be referenced elsewhere in the program by its name, or an individual element can be identified by means of integer values called indices that specify the row, column, and so on desired. The start of the indices will either be a 0 or 1 depending on the language. For example, the first element in a Python array is identified by an index of 0. In contrast to an array in which all data items are the same type, an aggregate type, also called a structure, a record, or sometimes a heterogeneous array, is a block of data in which different elements can have different types. For instance, a block of data referring to an employee might consist of an entry called name of type character, an entry called age of type integer, and an entry called skill rating of type float. The code shown in this figure is an example in the C programming language of how this aggregate type would be declared. The code states that the variable employee is to refer to a structure consisting of a 3-component called name, a string of 25 characters, age, and the skill rating. Once such an aggregate has been declared, a programmer can use the structure name employee to refer to the entire aggregate, or can reference individual fields within the aggregate by means of the structure name followed by a period and the field name, such as employee.age. The most basic imperative statement is the assignment statement, which requests that a value be assigned to a variable, or more precisely stored in the memory location identified by the variable. Such a statement normally takes the syntactic form of a variable, followed by a symbol representing the assignment operation, and then an expression indicating the value to be assigned. The semantics of such a statement is that the expression is to be evaluated and the result is stored as the value of the variable. Note the difference in how the assignment statement varies across languages. A control statement alters the execution sequence of the program. Of all the programming constructs, those from this group have probably received the most attention and generated the most controversy. The major villain is the simplest control statement of all, the goto statement. It provides a means of directing the execution sequence to another location in the program that has been labeled for this purpose by a name or number. It's a direct application of the machine-level jump instruction. The problem with such a feature in a high-level programming language is that it allows the programmers to write a rat's nest-like the top example of code versus the simplified second example. To avoid such complexities, modern languages are designed with control statements that allow an entire branching pattern to be expressed within a single lexical structure. The result is the practice known as structured programming, which encompasses an organized design methodology combined with the appropriate use of the language control statements. We have previously reviewed two popular branching structures, the if-else and while statements. These are present in almost all imperative, functional, and object-oriented languages. The examples on this slide could each be simplified using while statements as shown on the next slide. For Java and are identical in C, C++, C#, and Java, and for Ada, note that the fact that the identical nature of the C, C++, and Java statements is a consequence of the fact that C++, C#, and Java are object-oriented extensions of the imperative language C. Another common branching structure is often represented by a switch or case statement. It provides a means of selecting one statement sequence among several options depending on the value assigned to a designated variable. For example, the statements shown as an example on this slide. These code examples execute statement A, statement B, or statement C, depending on whether the current value of variable is A, B, or C, respectively, or execute statement D if the value of variable is something else. Still another common control structure, often called the for loop, is shown in this figure along with its representation in the C family, which is C#, C++, and Java. This structure differs from the Python for structure. Instead of implicitly setting up the initialization, modification, and termination components for a loop that iterates through a list of data, the C family for structure explicitly incorporates initialization, modification, and termination of the loop in a single statement. Such a statement is convenient when the body of the loop is to be performed once for each value within a specific range. Specifically, the statements in this figure direct that the loop body be performed repeatedly, first with the value of count being 1, then with the value of count being 2, and again with the value of count being 3. Programming languages that incorporate both kinds of for structure may differentiate between them with syntax such as for each or for in, F-O-R-I-N. Another important thing is, you need to pay attention to the evaluation order of the three expressions in the loop statement. So you need to try to rewrite the loop using while or repeat, so you will understand the evaluation order better. No matter how well a programming language is designed and how well the language's features are applied in a program, additional information is usually helpful or mandatory when a human tries to read and understand the program. For this reason, programming languages provide ways of inserting explanatory statements called comments within a program. These statements are ignored by a translator, and therefore their presence or absence does not affect the program from a machine's point of view. There are two common ways of inserting comments within a program. One is to surround the entire comment by special markers, one at the beginning of the comment and one at the end. The other is to mark only the beginning of the comment and allow the comment to occupy the remainder of the line to the right of the marker. The concept of a function is the major technique for obtaining a modular representation of a program in an imperative language. Programming languages have used many terms for this essential concept: subprogram, subroutine, procedure, method, function, sometimes with subtle differences in the meaning. Among the strictly imperative languages, the term function has come to predominate, whereas in object-oriented languages, the term method is used. A function in its generic sense is a set of instructions for performing a task that can be used by other program units. Control is transferred to the function at the time its services are requested and then returned to the original program unit after the function has finished. The process of transferring control to a function is often referred to as calling or invoking the function. We will refer to a program unit that requests the execution of a function as the calling unit, as will be shown on the next slide. Functions are usually written as individual program units. The unit begins with a statement known as the function's header that identifies, among other things, the name of the function. Following this header are the statements that define the function's details. These statements tends to be arranged in the same manner as those in a traditional imperative program, beginning with declaration statements that describes the variables used in the function, followed by imperative statements that describe the steps to be performed when the function is executed. As a general rule, a variable declared within a function is a local variable, meaning that it can be referenced only within that function. This eliminates any confusion that might occur if two functions written independently happen to use variables of the same name. Variables whose scopes are not restricted to a particular part of a program are called global variables. Most programming languages provide a means of specifying whether a variable is to be local or global. Functions are often written using generic terms that are made specific when the function is applied. Such generic terms within functions are called parameters. The terms used within the functions are called formal parameters, and the precise meanings assigned to these formal parameters when the function is applied are called actual parameters. The task of transferring data between actual and formal parameters is handled in a variety of ways by different programming languages. In some languages, a duplicate of the data representative by the actual parameters is produced and given to the function. Using this approach, any alterations to the data made by the function are reflected only in the duplicate. The data in the calling program unit are never changed. We often say that such parameters are passed by value. Unfortunately, passing parameters by value is inefficient when the parameters represent large blocks of data. A more efficient technique is to give the function direct access to the actual parameters by telling it the addresses of the actual parameters in the calling program unit. In this case, we see that the parameters are passed by reference. Passing parameters by reference allows the function to modify the data residing in the calling environment. As this figure shows, control is transferred to the function at the time its services are required and then returned to the original program unit after the function has finished. The process of transferring control to a function is often referred to as calling or invoking the function. The calling unit is the program unit on the left that requests the execution of a function on the right. Once the function on the right completes, control is passed back to the calling unit. Although not shown in this figure, the calling unit could have passed parameters to the function which could have been local or global. Figure 6.9 presents the definition of a function named project population as it might be written in the programming language C. The function expects to be given a specific yearly growth rate when it's called. Based on this rate, the function computes the projected population of a species, assuming an initial population of 100 for the next 10 years, and stores these values in a global array called population. If we call the function by project population, parenthesis 0.06, close the parenthesis with a semicolon, and then we can put a comment here, which is 0.06 is an actual parameter. Then the actual parameters can correspond to formal parameters by positions when there are multiple parameters associated with a procedure. At times, the purpose of a function is to produce a value rather than perform an action. The term fruitful function is sometimes used to differentiate functions that do specify a return value. Regardless of the language's specific terms, most languages have names of the same concept, a program unit that transfers a value back to the calling program unit as the value of the function. That is, as a consequence of executing the function, a value will be computed and sent back to the calling program unit. This figure represents a definition of a function named cylinder volume, as it might be written in the language C. When called, the function receives specific values for the formal parameters, radius and height, and returns the result of computing the volume of a cylinder with those dimensions. As an example of passing by value versus passing by reference, let us suppose that the function demo was defined as def demo, parenthesis formal, close parenthesis and then colon, and then we say formal equal formal plus 1. Moreover, suppose that the variable actual was assigned the value 5, and we call demo with the statement demo parenthesis actual, and we close the parenthesis. If the parameters were passed by value, the change to formal in the function would not be reflected in the variable actual as shown in this figure. If parameter passing is by value, the communication between caller and callee is one way from caller to callee. If parameters are passed by reference, the value of actual would be incremented by 1 as shown in this figure. Two-way communication between caller and callee can be achieved by pass by reference. The process of converting a program from one language to another is called the translation. The translation process consists of 3 activities: lexical analysis, parsing, and code generation, that are performed by units in the translator known as the lexical analyzer, parser, and code generator. Let's look at the translation process. The program in its original form is the source program. The translated version is the object program. Lexical analysis is the process of recognizing which strings of symbols from the source program represent a single entity or token. For example, the 3 symbols 153 should not be interpreted as A1, A5, and A3, but should be recognized as representing a single numeric value. Likewise, a word appearing in the program, although composed of individual symbols, should be interpreted as a single unit. Most humans perform lexical analysis with little conscious effort. When asked to read aloud, we pronounce words rather than individual characters. The parser views the program in terms of lexical units tokens rather than individual symbols. It's the parser's job to group these units into statements. Indeed, parsing is the process of identifying the grammatical structure of the program and recognizing the role of each component. The final activity in the translation process is code generation, which is the process of constructing the machine language instructions to implement the statements recognized by the parser. Let's look at some examples. This figure shows a syntax diagram of the if-else statement from Python. This diagram indicates that an if-else structure begins with the word if, followed by a Boolean expression, followed by a colon, followed by indented statements. This combination might or might not be followed by the word else, a colon, and indented statements. Notice that terms that actually appear in an if-else statements are enclosed in ovals, whereas terms that require further description, such as Boolean expressions and indented statements, are enclosed in rectangles. Terms that require further description, those in rectangles, are called non-terminals. Terms that appear in ovals are called terminals. In a complete description of a language's syntax, the non-terminals are described by additional diagrams, i.e. a decomposition. As a more complete example is shown in this figure, which presents a set of syntax diagrams that describes the syntax of a structure called expression, which is intended to be the structure of simple arithmetic expressions. The first diagram describes an expression as consisting of a term that might or might not be followed by either a plus or minus symbol, followed by another expression. The second diagram describes a term as consisting of either a single factor or a factor followed by a asterisk or division symbol, followed by another term. Finally, the last diagram describes a factor as one of the symbols x, y, or z. The manner in which a particular string conforms to a set of syntax diagrams can be represented in a pictorial form by a parse tree, as demonstrated in this figure, which presents a parse tree for the string x plus y times z based on the set of diagrams from the previous slide. Note that the tree starts at the top with the non-terminal expression, and at each level shows how the non-terminals at that level are decomposed until the symbols in the string itself are obtained. In particular, the figure shows that an expression can be decomposed as a term followed by the plus symbol followed by an expression. In turn, the term can be decomposed as a factor, which turns out to be the symbol x, and the final expression can be decomposed as a term, which turns out to be y times z. The process of parsing a program is essentially that of constructing a parse tree for the source program. Indeed, a parse tree represents the parser's interpretation of the program's grammatical composition. For this reason, the syntax rules describing a program's grammatical structure must not allow two distinct parse trees for one string, since this would lead to ambiguities within the parser. A grammar that does allow two distinct parse trees for one string is said to be an ambiguous grammar. Ambiguities in grammars can be quite subtle. As an example, parsing of the statement if b1 colon, if b2 colon, s1, else colon, s2 can be interpreted in two different ways, as shown by the diagram on the right. Note that these interpretations are significantly different. The first implies that statement S2 is to be executed if B1 is false. The second implies that S2 is to be executed only if B1 is true and B2 is false. The syntax definitions of formal programming languages are designed to avoid such ambiguities. In Python, we avoid such problems by using indentation, as shown by the lower code sample, and parsing diagram. The steps of lexical analysis, parsing, and code generation in a translation process are not carried out in a strict sequential order. Instead, these activities are intertwined. The lexical analyzer begins by reading characters from the source program and identifying the first token. It hands this token to the parser. Each time the parser receives a token from the lexical analyzer, it analyzes the grammatical structure being read. At this point, it might request another token from the lexical analyzer, or if the parser recognizes that a complete phrase or statement has been read, it calls on the code generator to produce the proper machine instructions. Each such request causes the code generator to build machine instructions that are added to the object program. In turn, The task of translating a program from one language to another conforms naturally to the object-oriented paradigm. The source program, lexical analyzer, parser, code generator, and object program are objects that interact by sending messages back and forth as each object goes about performing its task, shown in this figure. The object-oriented paradigm entails the development of active program units called objects, each of which contains functions describing how that object should respond to various stimuli. The object-oriented approach to a problem is to identify the objects involved and describe them as self-contained units. Consequently, object-oriented programming languages provide statements for describing objects and their behavior. In this section, we will introduce some of these statements as they appear in the languages C++, Java, and C#, which are the three of the more prominent object-oriented languages used today. In the object-oriented paradigm, a template for a collection of objects is called a class. A class describes the common characteristics of a collection of objects. A class is like a factory where objects can be created, and each of them can act upon same messages received from others. In object-oriented programming, each object has its own state, which is represented by instance variables defined in a class. A variable that resides with an object is called an instance variable, and the functions within an object are called methods or called member functions in the C++. A constructor is a special method which is used to create an object from a class and initialize the object state. As an example, in this figure, a class named laser class describing the structure of a laser in a computer game is outlined. The class consists of the declaration of a variable named remaining power of type integer and the three functions named turn right, turn left, and fire. These functions describe the routines to be performed to accomplish the corresponding action. Thus, any object that is constructed from this template will have these features: a variable called remaining power and the three functions named turn right, turn left, and fire. Note that in this figure, the instance variable remaining power is described using a declaration statement, and the methods are described in a form reminiscent of the functions. Declarations of instant variables and descriptions of methods are basically imperative programming concepts. When an object is constructed, often some customizing activities need to be performed. For example, we might want different lasers have different initial power settings, which would mean that the instance variable named remaining power within the various objects should be given different starting values. Such initialization needs are handled by defining special methods called constructors within the appropriate class. Constructors are executed automatically when an object is constructed from the class. A constructor is identified within a class definition by the fact that it is a method with the same name as the class. This figure presents an extension of the laser class definition previously shown. Note that it contains a constructor in the form of a method named laser class. This method assigns the instant variable remaining power the value it receives as its parameter. Thus, when an object is constructed from this class, this method will be executed, causing remaining power to be initialized at the appropriate setting. To simplify the description of objects with similar yet different characteristics, object-oriented languages allow one class to encompass the properties of another through a technique known as inheritance. The customized interpretation of a method call or message is known as polymorphism. The message is said to be polymorphic. We will cover the concepts of inheritance and polymorphism in more detail later in the course. Another characteristic associated with object-oriented programming is encapsulation, which refers to restricting access to an object's internal properties. To say that certain features of an object are encapsulated means that only the object itself is able to access them. Features that are encapsulated are said to be private. Features that are accessible from outside the object are said to be public. As an example of encapsulation, let us return to our previously outlined laser class. Recall that it described an instance variable remaining power and the three methods: turn right, turn left, and fire. These methods are to be accessed by other program units to cause an instance of laser class to perform the appropriate action, but the value of remaining power should only be altered by the instance's internal methods. No other program unit should be able to access this value directly. To enforce these rules, we need merely designate remaining power as a private and turn right, turn left, and fire as public as shown in this figure. With these designations inserted, any attempt to access the value of remaining power from outside the object in which it resides will be identified as an error when the program is translated, forcing the programmer to correct the problem before proceeding. We will revisit many of these concepts later in the course, particularly during the object-oriented programming lecture, which will include additional reading reference materials. So that wraps up this lecture. I know that was rather fast kind of going through it. Some of the slides you may need to review in more details as they require another pass through. So this concludes the lecture, and certainly you can email me questions after watching this recording. And in the next module, we will begin our initial exploration of the Python programming language.